So here's another example of a resolution problem where we're going to look at how the pupil size of an animal seeing things at a distance affects how well it can resolve objects on a road. Okay, so here's a common example that would happen in Canada. You're driving along at night and then bow, a deer jumps on the road and can cause actually a life-threatening situation for both you and the deer. Deer have incredibly large eyes, okay, and have very large pupils on the order of 1 centimeter. On the other hand, humans, our pupil size is around two millimeters. Okay, so how does having an increased pupil size affect the ability for a deer to see things at a distance and see things clearly at a distance? That's what this problem is going to be taking a look at. Okay, so the problem is similar to one that you have in your textbook in SOCOS, where the headlights of a car are 2 meters apart. A deer on the road has eyes with a pupil size of 1 centimeter. Suppose that light coming from the car is 500 nanometer wavelength. That would be the maximum wavelength. Estimate the maximum distance at which the two headlights are seen as distinct. Okay, so before solving this problem, let's draw the situation. Okay, so if I had here's a bad version of a car, but these are the headlights on the car. And these headlights are 2 meters apart. Okay, and the deer is somewhere over here and has a very large eye, okay, with, I use that color, okay, that is going to be 1 centimeter in depth is equal to B, okay, so the slit width there is 1 centimeter. Remember, it's a circle, so it's going to have a different equation. And what happens is the light from this headlight enters that pupil and heads off in that direction. The light from that headlamp enters the eye and ends up somewhere over here. Okay, and remember, resolution is caused by the overlap of those diffraction patterns. So what we want to know is, using Rayleigh's criterion, is what is going to be the distance, the maximum distance, such that the central maximum formed by that source of light is going to overlap the first order minimum, okay, of the other source of light, if you remember that. Okay, that's Rayleigh's criterion. And the most important thing that you would remember from Rayleigh's criterion is the actual formula. Okay, so in this situation, because it's a circular aperture, okay, that's because the eye has a circular aperture. Notice that animals kind of have a cross between a circle and a square. It's kind of different. So I wonder if the formula really fits, but we're going to assume it's a circular aperture. Okay, and in that case, you remember this formula. The minimum angle that those two light sources can subtend on the eye is going to be equal to 1.22 lambda over B. Okay, so the minimum angle, that's the angle that is being subtended by, that's the angle that's being subtended by those two headlights on the pupil of the eye, and that angle is going to be the same as that angle. Okay, that minimum angle is derived by that. Okay, so if I plug in the numbers, or before even doing that, that angle here that is being subtended by these headlights can be calculated using this. Okay, where S is the separation of the headlights, X is going to be the distance or the radius. So, and then remember that that's in radians. That angle is measured in radians. Okay, so knowing that, okay, I can substitute S over X is equal to 1.22 lambda over B. So in order to calculate that distance, that maximum distance, I'm going to rearrange this entire formula. So S times B divided by 1.22 lambda is going to be equal to X. And in order to calculate that, I will do that right now. All right, so S is 2 meters. B is 0.01 meters. It's a 1 centimeter distance. 1.22 times 500 times 10 to the minus 9 meters is going to be equal to X. So 2 times 0.01 is going to be 32.8 kilometers is equal to x, okay? So we would have calculated 32.8 kilometers is equal to x. Now, if you take a look at this problem, the similar problem, so on page 378 of your text, if you take a look at problem 9.15, you would find that the human eye under the same conditions would see 7 kilometers, okay? Because the human eye has a 1 millimeter or 2 millimeter, okay, diameter. So the difference there is that an animal would resolve images at a further distance than the human eye. So going back up here, animals that have very large pupil sizes, such as owls or predatory birds, they can resolve things at a much further distance than human can, okay? And that's an adaptation that evolved over time because these animals need to hunt, okay? On the other hand, deer need to run away from predators, okay? So they need to be able to resolve a lion in the grass or certain things, okay? And so they need very large pupil sizes. During the daytime, where there's a lot of sunlight, animals with large pupils get blinded, okay? So they would be moving around more at nighttime, so they could have better resolution. During the daytime, when you have a lot of sunlight, the pupil is going to constrict and become smaller. So the vision of these animals get worse during the daytime, but are much better at night. So you'll see them foraging around more at night. That's why it's dangerous to drive on a road at nighttime. Owls hunt at night because they will see better at night during the day. All right, so a lot of predators are nocturnal for that reason, that they can increase the pupil size and have better resolution. Okay, an owl can fly a kilometer above the ground and see a mouse in the grass and come down at it. So that's fascinating. So as we increase the diameter, we will have better resolution. If I increase the diameter of the pupil, I'll have better resolution because I'll minimize my diffraction. Okay, on the other hand, the next questions are going to look at how can I get better resolution by changing the wavelength of light that I'm using.